Okay, we're at the next section, the Ray approximation in geometric optics. And before we get to the PowerPoint slide, I want to show you this image, because if you imagine putting a candle in a room and you look at it from overhead, you would imagine that the lights would scatter in this sort of form. Just uh, the light intensity real near the center of the candle, and as they radiate outward, they get dimmer and dimmer and dimmer. But right now, ignoring uh, the fall off of intensity with distance, let's just think of this. Let's use your imagination and think of what happens. Well, let's say this is just 1 meter away, but think of it. What if you were 100 meters, and what if you were 200 meters? What if you were a kilometer? What would these waves look like? And they would look more like what we see at the start of our chapter here. Um, the 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 rays would be straight lines. You can imagine here, way off to my left is where this candle is, or we could just say the sun. It's nice and intense. So these light rays would be coming in parallel, and you have these beige plates would be like the wave fronts. Let's read the green box. The rays are straight lines perpendicular to the wave fronts and pointing in the direction of the wave motion. So this is the way we imagine waves when we study reflection and refraction. So this is the image we want to have, not the image I showed you earlier of the circular, like waves on a drop of a pebble in a pond, and these waves radiate outward. So we're not in the near field, we're in the far field, where the rays are parallel, and their perpendicular wave fronts are along uh, the path of the rays. And so we see this, we see these waves coming in and hitting the plate, and all being directed away from it. And this is reflection. This is specular reflection. And it shows it in the red image down here. Specular reflection, where you have a nice smooth surface, everything gets reflected, and you can get like a mirror image of what's being, uh, the light image coming from the far field. On the right in B is what we call specular reflection, where it's kind of rough, and so it's kind of diffuse, and it goes in all sorts of directions. And if you have like a rough desktop, it would be the difference between, I have a light here above me, and if I were to hold a mirror, I would get all the light. If I were to hold a piece of paper, that would be diffuse. I wouldn't. You might see some reflection, but it would be much more diffuse than if it were, say, like a mirror. So we have two different types of reflection: specular and diffuse reflection. Now, I exposed you to this a little bit at the beginning. This is the law of reflection. The incident ray, the reflected ray, and the normal all lie in the same plane, and theta 1 equals theta prime 1. And so this is the incident ray. Remember at the beginning they showed you a light coming in at 60 degrees, and the reflected ray was at 60 degrees. So the incident ray and the angle of the incident ray and the angle of the reflected ray are equal. Theta 1 equals theta prime 1, or theta 1 prime, if you want to say it that way. So that is the law of reflection. Now let's talk about, okay, here it is. The angle of incidence equals the angle of reflection. Theta 1 equals theta 1 prime. Okay, now let's look at refraction of light. All rays in the normal lie in the same plane, and the refracted ray is bent toward the normal because V2 is less than V1. What is V1 and V2? Well, V1 is the speed of light in the first medium, in this case air, and V2 is the velocity of light in the second medium, in this case, glass. So the incident ray comes in, and it hits the glass, and it starts going slower, and so it's refracted, and you get this bending of the light beam. And they show it here. One is the incident ray. Two is the reflected ray. Three is the refracted ray. And then four is the reflection off of this bottom surface. And then five is the refracted ray as it goes from glass back to air. And it looks like the angle here is the same as the angle there. You can see these look parallel. So all rays in the normal lie in the same plane, and the refracted ray is bent toward the normal because V2 is less than V1. Okay, let me make sure I'm up to speed on my notes. Okay, so sine theta 2 over sine theta 1 is equal to V, the velocity of 2 over the velocity of 1, and that's a constant. And we're going to learn about those constants. We're going to learn about that constant of proportionality, and it's related to the index of refraction. Now, the path of light ray through refracting surface is reversible, and you can see the reversibility here. From 1 to 3, it's reversing from 4 to 5. Okay, and let's see. When the light beam moves from air into glass, its path is bent toward the normal. You can see that here. It's theta 2 is less than theta 1. The way they have it expressed here, theta 1 is greater than theta 2 because V2 is less than V1. Now, as it comes out of the glass, when the beam moves from glass into air, its path is bent away from the normal. It's not shown here, but theta 2 is going to be equal to theta 1. This theta 1, maybe I shouldn't have said that. This right theta 2 is going to equal this left theta 1. Okay, and I think that might be it for this. We'll go on with the law of refraction in the next section.